All right, so we'll go to the next speaker, Sreenath, the director of Lekha Wireless. So I try to accommodate the speakers who are from Far East, like China, India, in the early morning, because it's late night there, late evening, I should say. So I hope folks on site appreciate that. So machine intelligence and radio access networks, Sreenath, Dr. Sreenath Ramanth is the director of wireless. And brief introduction. He got his master's from IISc Bangalore and a PhD from India, France. He is now as a director with Lekha Wireless. He has led many R&D standardization efforts, including GPS, CDMA, wireless LAN, WiMAX. Has been an associate researcher with Bell Labs as well, adjunct faculty at IIT Mumbai, and currently serves at the Governing Council of TSDSI, which is the Telecom Standards Development Society of India, within the umbrella of 3GPP, senior member of IEEE. Sreenath, if you're ready, you can please proceed with your presentation. You have 20 minutes. Just to let you know, you try to manage your talks within that time. Thank you.
Yeah, thank you, Ashutosh. Hope I'm audible.
Yes, you are. Go ahead, please.
Yeah, thank you for this opportunity. And then I will just get into the presentation.
Yeah, put it in the presentation mode, please.
Yeah, just trying to do that. Yeah. Sorry for the small hiccup. Once again, I would like to thank Dr. Ashutosh, IEEE Standards Association, and all the people who have joined in various time zones to listen to this brief talk. In fact, I think when I just start, so basically I would also like to draw your attention to the previous speakers who actually went in quite some depth in a lot of topics like Shane Lin and Charles. They already would have given most of the people a very good overview. In fact, I think my talk is a little more basic because I come from a company which is about a decade old. We at Lekha focus on telecom, defense, and then also on industrial IoT. So we have been into this with 4G and then now designing and developing products in the 5G era. So this is a quick introduction. So this is my top overview. So I hope this is mostly for the, somebody who is more recently into the RAN activities and some of the experts that we just hired. Okay, so basically I thought I'll just cover a brief history of RAN, then get a little bit into RAN architecture and categories, and a bit more into the machine intelligence part where we discuss few use cases, applications, and the framework. A little bit of deployment and what is on 3GPP. Of course, our first speaker spent a lot of time and then really went into depth on a lot of topics. So this is more like possibly a little bit of revision and also at a very basic level. Okay. So I just started with some history, basically where 2G was functionally architecture was static. Okay. And most of the functionalities were geographically localized. Okay. And most of the radio was within a base station. Then in 3G, okay, we split the radio functionality. So transmission, reception, which were the responsibility of the node B. And then the radio resource management and higher layer RAN, okay, processing in radio network controller. Then LTE Advanced came upon and then 4G changed the expectations on the transfer, data transfer rate and security. So this is where the evaluation started. So basically, if you look at the slide here, basically we have the baseband unit and the radio resource head, okay. So you have the core network to which multiple base stations are connected through the backhaul, and then to the BBU, we interface with the RRH. So this is the basic thing which most of the people here are aware of. Okay. So the problem with this was a kind of low spectral efficiency, high cost of scaling the architecture, and inefficient use of resources. So next came the Cloud Run, okay, where like we could decouple the RRUs and the corresponding BBUs. So like even like the previous speaker spoke and also the others, RRUs stay at the cell site in this architecture and connect a centralized but shared and virtual group of BBUs. So basically the difference is that like, okay, functionalities related to layer one, that's the physical layer, such as sampling, modulation, okay, resource block mapping, etc., like kind of moved into the moved into a separate virtualized framework. So that's the cloud framework. So next we go into the virtualized RAN, like okay, which was a very revolutionary improvement in networking. So basically, it's a disaggregated RAN architecture, okay, where the software is separated from the underlying hardware. This modification makes it possible to run functionalities dynamically and flexibly. So it reduces the cost of maintenance and operation because a modification of network functionalities does not require hardware-related amendments. Functions can run on common off-the-shelf hardware. Okay, so we ran. Let's the way to open run. I think that's the whole forum where like okay, we are discussing about a lot of things. So this is a multi-vendor architecture, like the previous speaker could actually bring in a more pictorial way, like okay, how it's a multi-vendor architecture. So this means that Open RAN, okay, commands compatibility between components built by different vendors. So interoperability and reliability in Open RAN demands a global standard. So that's how the ORAN Alliance was formed, and it has grown to a very big in strength. So the software community that works on building Open RAN components and creates frameworks for different use cases. And then we have the TAP Open RAN, disaggregated and interoperable, all Gs, okay, solutions for Open RAN. And then the Open Network Foundation that created the SDRAN to implement near real-time controller solutions. Now coming into a bit of architecture, like okay, disaggregation of RAN, hardware and software on vendor-neutral TGPP-based platforms. Open interfaces between components, example, RU, CU, DU, RAN intelligent controller, flexibility in separation or aggregation of components, adoption of new technologies such as machine learning and artificial intelligence, which we are going to shortly talk about a bit, and multi-vendor approach for supplying components. So basically, if you look at the architecture itself, I think most of the people here may be aware of this, but I'm just flashing this slide. So basically, we have the service management and orchestration framework. And then we have the near real-time intelligent controller and the non-real-time intelligent controller. Of course, we have the ORU, ODU, and then like, okay, we have the OCU, UP, OCU, CP, and OE node B, and all the interfaces that go along with O1, O2. So like, okay, basically the picture on the right though may not be very clear, but captures the overall essence of the architecture of Open RAN. And then we have the O Cloud, which is a collection of physical infrastructure nodes that host the ORAN, okay, such as the near RT, RSC, OCU, CP, OCU, UP, and ODU. The management and orchestration related functions and the underlying software components. Okay, so this is again a quick a snapshot of the same, like, okay, not possibly going to go deep into it, but just to give you an idea. Then what are the categories? So basically, I think at a very high level, we have three categories. So real-time controlling applications that run on the DU. The latency for these controllers is expected to be less than 10 milliseconds. Then we have the near real-time applications with the latency less than 1 second. And the third category where you have the non-real-time intelligent controllers with more than 1 second. So where is the best place within the Open RAN architecture to execute these applications is the common question. Coming to like, okay, I just want to move into the machine learning part. Like, okay, I think now machine learning is a critical part of all, the next generation of networks. So a quick thing like, okay, we know the classifications like, okay, supervised learning, unsupervised learning, reinforcement learning. So basically like, okay, I'm not going very much into depth about the variations, but I think most of the people here would be aware of it already. So I also just give you a quick snapshot in the right about the telecommunications where all it is applicable, like quality of service, quality of experience, fault prevention, handover, traffic steering, slicing, okay. Then beamforming. And if I really categorize, like, okay, for example, look at supervised, unsupervised, and reinforcement, we can also look at like the kind of algorithms that we typically come across. Okay, so I just mentioned them. Okay, what are all the popular? So this is just trying to kind of give an idea on the applications and the categories, the basic categories of machine learning, and then what are the kind of the algorithms that go in there. So coming to the, okay, in the Open Run initiative, so possibly, okay, this is taken from a reference. So basically we have supervised, unsupervised, combined, on the other hand, reinforcement, or a combination of all three. And we have various applications, like, you can take any examples, like for example, if you look at MIMO applications, it could be combined traffic steering. So here, there's always like a scope to kind of have different mechanisms or a combination thereof for any implementation. Okay, so this is still an evolving thing. So just trying to give a picture of how all of them can come together into various possible applications. So that is what this slide tries to cover. So for example, suppose I consider the first use case, like, okay, where we are trying to look at the network efficiency. So we have a city area, we have a suburban area. So, like one can kind of come with a possibility that, like, okay, when the traffic load in the cities increase, typically the suburban traffic load would be reduced. And then, like you can see at the edge, like, okay, when the suburban traffic actually increases, this is an example from a reference. So basically, based on that, like, okay, a lot of efficient management can happen, between network energy efficiency can be improvised. Similarly, like, okay, we look at load balancing, in which case, like, okay, the cells which are low traffic, less traffic, and they can be offloaded with users from the cells with more traffic. It's also another example case here. Then if you look at mobility management, okay, the scheme to guarantee the service continuity during the mobility by minimizing the call drops, reducing failures, handovers, and ping pong. For the future high frequency network, as the coverage of a single node decreases, the frequency for UE to handover between nodes becomes high. In addition, for the applications characterized with a stringent quality of service requirements, such as reliability, latency, the quality of experience is sensitive to the handover, so that mobility management should avoid unsuccessful handover. Okay. Also coming to the MAC layer functions and URLs, see just few points here, like, okay, where MAC scheduler assigns resources to user devices and ensures QoS. MLA incorporate with MAC scheduler tasks such as link adaptation, massive MIMO, and multi-user MIMO. Cognitive MAC layers to predict use mobility patterns, where again your machine intelligence comes into picture. Based on the report, MAC layer general tasks and model predictions compete for resources with 10 milliseconds. It's a challenging task. Coming to RLC, like again, use cases such as V2X, mission critical applications and all, okay, require a lot of, machine intelligence, and then like, okay, this also has to be part of the, access network. And coming to the handoff, again, as another use case, okay. So basically, like, okay, we'll monitor the device specific mobility, predict or detect unexpected handover events, and generate sequences to prevent anomalies. Again, we have traffic steering, again, constantly monitors users and ensures, like, okay, KPIs of QA are met. Running traffic steering relies on the historical data. near RT, RAC can access this information from SMO, and non-real-time RAC or are not limited, uses the same host to collect and use this data. So basically optimize use receive signal strength and energy consumption of batteries. So what are the use cases like data governance analysis, management and orchestration, network storm protection and control, dynamic handover management, EOV applications, traffic steering, optimization of massive MIMO, network slicing. These are all some of the use cases. Okay. And then what are the applications? So basically distributed cloud, where we have the central edge clouds for end-to-end optimization, disaggregated network where virtualized and disaggregated RAN for network and device optimization, edge devices on device intelligence for local device optimization. Okay. Then what are the advantages of on-device AI? So enhanced device experience, more intelligent beamforming and power management, improved throughput, robustness and battery life, improved system performance, on-device interference, reduces network data traffic for more efficient mobility and spectrum utilization, better radio security, detecting and defending against malicious base station spoofing and jamming with fingerprinting, spectrum sensing and access, predict activities of other devices for more efficient access and better scheduling to improve edge system performance. And the environment sensing, so ISAC has been one of the most promising areas going further. So this also would benefit in terms of detect gestures, movements, and objects by monitoring signal reflection patterns to enable new use cases.
Sreenath, you have about 5 minutes or so.
Yeah, sure, thanks. So what are the kind of steps that we do? First, offline learning must occur before deployment within a network, as most common algorithms need a certain level of seeding before deployment. Second, AML models are trained through a combination of supervised, unsupervised, and reinforcement learning. Third, AML algorithms are implemented in a modular manner to allow for independence. Lastly, VORA and its open interfaces allow for vendor-specific AML algorithms within each model, which is a very important feature. I think this diagram was also flashed some time before. So basically, just giving the functional framework for RAN intelligence. So this is taken from report 37.817. So you have the data collection, then the training data, model training, inference data, where model inference, and then the output goes to the actor, and then feedback. So this is a general framework. And also this is the workflow, where basically different components of the ML features are kind of coming into the SMO, non-RT RAC, near RT RAC, and how they are connected between each other. So coming to the support in 3GPP, I think already more details were provided by our first speaker. I'm just summarizing, or rather putting a few points. So RAN plenary approved a new study item to investigate support for AML in 5G RAN, explored a functional framework for RAN intelligence and different use cases based on the current 5G RAN architecture, where the application of AML techniques could bring substantial benefits. It is still an ongoing activity in a lot of, RAN and SA, arms of the 3GPP. The approval of the report study on enhancement for data collection for NR and ENDC was the first of its kind, and its outcomes are influencing work in similar activities of other work groups. Okay, so just mentioned a couple of them here. So these are the references, just before concluding the talk, I want to say that this is a very broad subject, and there have been many key people contributing here. I could not really cite all of them, but this is basically a summary of the evolution, the ORAN, its components, machine learning, what are the use cases, and what is the methodology going further, and what is the brief way in which things are kind of progressing in the 3GPP. So yeah, thank you for this opportunity. So this is possibly a little bit basic, but I hope it was useful to at least some of the people. Thank you all for your patience and then for the opportunity. Yeah, thanks.
Thank you, Dr. Sreenath. Let's give a round of applause for our speaker.